Welcome back to Electrochemical Engineering. Today I'm going to talk about porous electrode theory and how it applies to electrodes with flow. This is a nice diagram that I pulled from this publication. It shows the complexity of flow electrochemical reactors, particularly as applied to electrosynthetic applications. You can see that you typically have an anode and a cathode, both of which are porous. They have some structure to the electrode. That structure can be used to promote laminar, turbulent flow or other types of flow. There's typically a spacer. It can either be a divided cell or an undivided cell. There's electrolyte manifolds that distribute the electrolyte. You have to think about the hydraulics. You have to think about the electrical parameters, the reaction rates, the transport. All these things are incredibly complicated in engineered systems that drive electrochemical reactions at high rate. There are two types of electrochemical flow reactors that we're going to discuss. In this case, the fluid flow, here indicated by these arrows, is in the same direction as the current going from anode to cathode. This is called a flow through reactor. In another geometry called a flow by reactor, the fluid flow goes through the anode and the cathode, the porous anode and the cathode, while the current flows from anode to cathode orthogonal to the fluid flow. In these electrochemical reactors, we're going to assume some things. One of the things we're going to assume is migration is negligible. That's because the flow is handling most of the transport. We're also going to assume the flow velocity is constant throughout the entire reactor. This implies plug flow. So the velocity of the fluid is assumed to be constant across any cross section of the reactor or the pipe perpendicular to the axis of the flow. So the velocity fields here, if I write the velocity of each element of fluid moving, the velocity vectors are all the same. You might have learned about laminar pipe flow as an undergraduate if you're a chemical engineer. In that case, the velocity profile is parabolic, which is not something we're considering here. That's due to the no-slip boundary layer at the side of the pipe. So that sort of fluid flow would look more like this. The velocity vectors would have a parabolic shape as you move through the pipe. We're not going to consider that more complicated situation, but you could program that into a numerical solver like COMSOL. Let's consider an electrochemical flow through reactor. Here's an example where you're reducing copper 2+ to copper metal in this porous cathode. The current here is the anode, flows from the positive terminal of the anode to the negative terminal, which is the porous cathode. We're going to define x equals 0 for our differential equation at the front of the electrode. The back of the electrode is going to be defined as x equals L. Notice this is different than our definitions before. We can write a flux equation for the species A. The flux of species A, which is in this case the redox couple, A plus 2 electrons, has only two terms. It has a diffusion term and it has a convection term. We're going to ignore migration because of the large flow velocity. Vx is defined as the velocity of the fluid in the pores in the direction of interest, and epsilon times Ca, that's the average concentration within the electrode. Remember, Ca is the concentration that the electrolyte would have of species A, in this case copper 2+, that is getting reduced, if it was sitting by itself in a beaker, but epsilon is the porosity, it's the fraction of the electrode that actually contains that electrolyte. D effective is the effective diffusion coefficient, taking into account the tortuosity, the long path lengths within the porous electrode. dCA dx is the concentration gradient that's driving the diffusion process. Next, we're going to write a materials balance equation at steady state and solve that to find the concentration profile. At steady state, we can write that the time derivative, d dt, of the concentration of A in the pores has to be equal to 0. We can write that concentration change as in any given element as the change in flux across that element, what goes in minus what goes out, plus the local creation or destruction of A due to current. Here, A is the specific surface area, where Jn now is the species reaction rate. It's related to In, but in this case, Jn is in moles per area instead of current per area. We can write that term, Jn, equals Kc times Ca. Ca is the concentration as a function of x. Kc is the mass transfer coefficient. It's a little bit of a confusing name because it essentially relates the rate of the reaction to a combination of both kinetics and transport that both affect how fast A is consumed within this aggregate particle electrode. We can evaluate the change in flux of A with position using our equation for flux that we previously wrote. We're going to assume that diffusion is small relative to convection, and we've already discussed that migration is small. This gives us only the derivative of the convection term. All this is equal to 0 because we're at steady state where all time derivatives are equal to 0. We need to define some boundary conditions. These are pretty simple. The concentration of A at the front entrance is just the initial concentration. That's at x equals 0. All we have to do is separate these variables and integrate this differential equation. You should do that as a practice problem to find the solution. The concentration of A here as a function of x is just given by the initial concentration and this exponential decay term. Notice x is in the exponent of this exponential term. So as x increases, as you go further back in the electrode, the concentration exponentially decays. The decay constant alpha is defined here as the specific surface area, the mass transfer constant for the destruction of A, the velocity of flow, and the porosity. You can think about why these terms are related to the rate of utilization of A. If the specific surface area A increases, that provides more reaction sites for the reaction. If the mass transfer coefficient Kc increases, it increases the rate for a given concentration locally. If the porosity increases, it increases the fraction of electrolyte in the electrode and decreases the fraction of solid electrode. As the flow velocity increases, it gives less time for the reaction to occur. We can also write a charge balance equation to get the current. We assume that the desired reaction is the only reaction that takes place in the electrode. Note there's a discussion of side reactions in Fuller and Harp, and you can treat those cases as well. Here, this is I2, the derivative of I2 with respect to x. Remember, I2 is the current in the electrolyte. If the current in the electrolyte is changing with position, it must be due to a reaction. Here is the reaction rate, the electrochemical reaction rate, the Faradaic current, given as the product of the mass transfer coefficient and Ca, the concentration of A at that specific point x within the electrode. Now we can include explicitly the concentration of Ca based on our solution to the previous differential equation. And we know due to current continuity that the sum of these two terms must be equal to 0, so that the current is continuous throughout the entire electrochemical cell. Our boundary or auxiliary condition is that I2 equals 0 at the end of the electrode. That is, at the end of the electrode, the ionic current has to go to 0. We can easily solve this equation by separating and integrating to get I2 as a function of the concentration in, the position, and the length of the electrode. This is I2 again as a function of x. I2 at the beginning of the electrode is large. All the current is carried by I2 here. And at the back of the electrode, I2 is equal to 0. That's because there's no more Faradaic reaction happening beyond that. And that's all I wanted to discuss today for this topic.